Hey everyone, and welcome to The Explainer. Today, we're taking a massive dive into what is easily one of the most famous, universally applied rules in literally all of mathematics. Yep, we're talking about the Pythagoras Theorem. We're going to break down the geometry, unpack the proof step by step, and discover exactly why this ancient relationship is essentially the master key for understanding every single shape around us.
But before we start throwing formulas around, I want you to imagine a couple of real-world mysteries. Let's say you have a tall ladder leaning high up against a building. How do you figure out the exact ground distance from the wall if you can't actually get down there to measure it? Or let's bring it way closer to home. You're making a simple cheese sandwich, and you slice it diagonally. How do you mathematically calculate the exact length of that cut without ever touching a ruler? These aren't just annoying textbook problems, they are spatial puzzles that we can solve instantly once we have the right tool.
So here's our roadmap for today's explainer. First, what is Pythagoras Theorem? Second, visualizing the proofs. Third, triplets and the converse. Fourth, solving everyday math puzzles. And fifth, mastering complex shapes. Let's jump right in.
Section 1. What is Pythagoras Theorem? The ancient foundation.
Okay, so we all know it as the Pythagoras Theorem, obviously named after the famous Greek mathematician. But history actually gives us a really fascinating plot twist here. Long before Pythagoras came along, an Indian mathematician named Buddhayan actually mapped out this exact core relationship between the sides of a right-angled triangle, and he did this all the way back in 600 BC. So while Pythagoras definitely gets the modern branding, the foundation of this rule is incredibly ancient and actually spans entirely different historical cultures.
Right, so what is the actual rule? The strict definition states that in a right-angled triangle, the square on the hypotenuse is exactly equal to the sum of the squares on the remaining two sides. Now, as a quick refresher, the hypotenuse is always the longest side of a right-angled triangle. It's that slanted line directly opposite the 90-degree angle. Basically, if you square that long side, that final number will perfectly, flawlessly match the squares of the two shorter sides added together.
Moving on to Section 2. Visualizing the proofs. Seeing is believing.
Now, instead of just staring at algebra variables like a, b, and c, picture this. Imagine physically drawing actual, perfect squares attached directly to the three sides of our right-angled triangle. Suddenly, the geometry perfectly matches the algebra. You can clearly see the massive square built onto the long hypotenuse and the two smaller squares built onto the shorter legs. The theorem is literally telling us that if you took the physical area of those two smaller squares and squished them together, they would perfectly fill up the area of the massive square on the hypotenuse.
If we break down the logical flow of this area-based proof, it goes step by step to show us exactly why this magic works. First up, we draw those physical squares on all three sides. Second, we slice the biggest square by drawing a perpendicular line straight down through it. Third, by drawing a few clever diagonal connecting lines, we can mathematically prove that the newly formed triangles inside these shapes are congruent, meaning they are the exact same size and shape. And fourth, because those triangles are identical, we can logically prove that the areas of the split rectangles in that giant square are exactly equal to the area of the smaller side squares. Step by step, the complex geometry makes the algebraic formula completely undeniable.
But hey, there's actually more than one way to prove it. What if we try a completely different approach? Instead of drawing big, bulky boxes outside the triangle, let's just drop a single perpendicular line straight down from the 90-degree corner, right onto the hypotenuse. Boom! We instantly create two smaller mini triangles nestled inside the main one. And here's the cool part. Because they all share angles, these new tiny triangles are mathematically similar to the giant one, meaning their sides are strictly proportional to each other. By simply cross-multiplying the ratios of those proportional sides, we arrive at the exact same destination. The squares of the two shorter sides absolutely equal the square of the hypotenuse.
Section 3. Triplets and the converse. Math shortcuts. Now, this theorem is totally a two-way street. We've established that if a triangle has a 90-degree angle, the squares of the short sides will equal the square of the hypotenuse. But the converse rule tells us it works beautifully in reverse. Let's say you're looking at a totally random triangle, and you just happen to discover that the square of its longest side equals the sum of the squares of the other two. Well, congratulations. You've just proved that the triangle is absolutely flawlessly right-angled. It is literally a foolproof test for finding a true 90-degree corner.
And because this rule is so unbelievably strict, certain sets of numbers naturally lock together perfectly. We call these Pythagorean triplets. Think of them as the cheat codes of geometry. For example, if you have side lengths of 3, 4, and 5, well, let's do the math real quick. 3 squared is 9, 4 squared is 16,
Add 9 and 16 together and you get 25, which just so happens to be exactly 5 squared. It's perfect. Any multiple of these triplets acts as a lightning-fast shortcut. If you see a right triangle with sides 6 and 8, you instantly know the hypotenuse is 10. No calculator, no long division required.
All right, Section 4. Solving everyday math puzzles. Real-world geometry.
Let's go back to that mystery from the start. Imagine you have a ladder that is exactly 17 meters long. It's sitting in an alleyway between two buildings. When you lean it against the first building, it perfectly reaches a window that is 15 meters high. Now, keeping the feet of the ladder firmly planted in the exact same spot on the pavement, you swing it over to lean against the building across the street, where it reaches a window 8 meters high. The big question is, what is the total width of the street?
Well, because we know the length of the ladder, which acts as our hypotenuse, and we know the heights of the windows, we can just run our theorem in reverse to find those missing ground distances. For the first building, 17 squared minus 15 squared gives us the ground distance squared, which neatly works out to exactly 8 meters. For the building across the street, 17 squared minus 8 squared gives us a ground distance of 15 meters. We just add those two ground chunks together, 8 meters plus 15 meters, meaning the width of the entire street is exactly 23 meters. We literally just mapped physical reality using nothing but squares.
Let's bring this completely down to earth with a fun case study from the source text about Gita making a cheese sandwich. She takes a standard rectangular piece of bread and cuts it diagonally from corner to corner. By doing this, she instantly forms two perfect right-angled triangles.
Gita's sandwich has one short side measuring 4 centimeters and the longer adjacent side measuring 4 times the square root of 3 centimeters. So, what is the exact length of the longest side, that diagonal knife cut? Let's solve it right now. We square the 4 to get 16. Squaring 4 times the square root of 3 gives us 48. We add 16 and 48 together and we hit 64. And what is the square root of 64? Exactly 8. The hypotenuse of our lunch is exactly 8 centimeters long. Even a simple cheese sandwich bows to the rules of ancient geometry.
Which brings us to Section 5, Mastering Complex Shapes, Unlocking Geometry.
You might be wondering, how do we handle shapes that aren't right-angled triangles? What about a slanted parallelogram or a diamond-shaped rhombus? Well, it's actually incredibly simple. By drawing diagonal lines across these four-sided shapes, or just dropping perpendicular lines straight down from their corners, we instantly chop them up into multiple, easy-to-solve right-angled triangles. By figuring out the sides of these newly formed inner triangles, we can easily calculate the diagonals, the perimeters, and the total areas of the weird, complex outer shapes.
And honestly, this perfectly highlights the absolute core takeaway from today's explainer. Every complex shape is really just a series of right-angled triangles waiting to be solved. The Pythagorean theorem isn't just some niche, isolated formula strictly reserved for three-sided polygons. It is literally the foundational, underlying grid work for demystifying pretty much any shape in flat space. It is the true connective tissue of geometry.
So, as we wrap up this journey, spanning from 600 BC all the way to the sandwich sitting on your plate, I want to leave you with a bit of a challenge. Look around your room right now. Seriously, look at the corners of your ceiling, the tilt of your computer monitor, maybe the diagonal metal brace holding up your bookshelf. Where are the hidden right-angled triangles holding your world together? Because I promise you, once you start seeing them, you realize that with just a little bit of ancient math, you can measure absolutely anything. Thanks so much for joining me on this explainer. Keep looking for the angles out there, and I'll see you next time.